Has the idea of taking a stats class ever had you running away from potential majors like they were on fire? You're not alone. But here's the secret. Stats isn't about math for math's sake. It's about making sense of the world. And one of the most useful things you can learn, how to choose the right statistical test. From t-test, ANOVA, chi-square, regression. I'm Megan Puglia, and in this episode of Unhidden Curriculum, we're stripping away the jargon and equations to give you a decision-making toolkit that actually makes sense. Today, there's no formulas, just clarity. Okay, let's start here. Why do we even do statistics? Science is about answering real questions, not just going off vibes. But data doesn't speak for itself. It's messy, it's noisy, and it needs translation. And that's what statistics is, the translator that turns raw data into actual conclusions. Without stats, you're not doing science. You're just telling anecdotes with extra steps. At its core, statistics is about one thing: comparison. Stats lets us ask questions like, is group A different from group B? Is this pattern bigger than we'd expect by chance? Or is this trend real or just a blip in the data? It's all about comparing one thing to another with enough math to back it up. So whether you're comparing reaction times, brain volumes, growth curves, or bacteria counts, stats is how we figure out, is this difference real or is it just noise? But before you run any stats, you need to know, what kind of data are you working with? Not all data is created equal, and different types of data need different types of tests. Let's start big picture. There are two main kinds of data: quantitative or numerical data. This represents amounts or counts. You can do math on it. Then there's qualitative or categorical data. That represents labels or categories. You can group it, but you don't average it. From there, we break it down into 5 common variable types. First up are continuous variables. These are quantitative and can take on any value within a range. Think height, age, reaction time, or brain volume. Next are discrete variables. These are also quantitative but count-based. They only take whole numbers. For example, the number of siblings. Nobody has 2.5 siblings. Next is ordinal variables. These are ranked categories. They have a clear order, but the spacing between ranks isn't necessarily equal. Think first, second, and third born, or Likert scales like strongly agree and strongly disagree, or pain ratings. Next are categorical variables. These are qualitative and have categories that have no natural order. Think things like eye color, gender, or dog breed. Finally, there's binary variables. These are a special type of categorical. There's only 2 options: yes, no, true, false, or 0, 1. So why does this matter? Because the type of variable determines which type of test you can use. You can't compare apples to oranges or integers to adjectives. Trying to run the wrong test on the wrong variable is like using a hairdryer in the bathtub. It's not just unhelpful, it's dangerous for your conclusions. Now, it's important to know that every test comes with baggage, also known as assumptions. You don't need to memorize all of them, but here are a few usual suspects. First is normality. This is about the shape of your data. Ideally, your data should be roughly bell-shaped, also called a normal or Gaussian distribution. Think of it as most values clustering around the middle with fewer values at the extremes. Next is homogeneity of variance. This means your groups should have similar spreads or variability. If one group is super spread out and another is tightly clustered, that can mess with some tests. And finally, there's independence. This is the idea that each measurement should stand on its own, meaning one data point shouldn't influence or predict another. This assumption is crucial because many tests treat each observation as an independent voice in your dataset. An example is comparing reaction times between 2 separate groups of participants. Then there's also repeated measures designs. This is where the same person is measured multiple times. An example is pre- and post-test scores for the same participants. And finally, there's matched pairs. Here you have different people in each group, but they're closely matched or paired on purpose. Some examples are things like siblings, twins, or participants who have been matched by age and gender across groups. These assumptions help guide which statistical test to choose. But before you run your test, there's one more big question. Are you using a parametric or a non-parametric test? Parametric tests assume your data meets these assumptions: normal distribution, similar variances across groups, and independence. When these boxes are checked, parametric tests tend to be more powerful and precise. Non-parametric tests don't require those assumptions. They're more flexible, especially when your sample size is small or your data is weirdly shaped. Think of it like this: parametric is picky but powerful, non-parametric is chill but sometimes less sensitive. If your data violates the assumptions of a parametric test, it's not the end of the world. There's often a non-parametric version you can use instead, or transformations you can apply to your data to make it fit the assumptions. Okay, so now you know what kind of variables you have and you've checked your assumptions, you're ready to actually choose your test. Instead of memorizing formulas, I'm going to walk you through one of my favorite statistical resources, the What Statistical Test Should I Use Decision Tree Flowchart from the Stats in R blog by Antoine Sotui, which is linked in the description below. The first step in deciding your statistical test is to determine how many variables are you analyzing. When you have one variable, you're usually asking, does my sample look like what I'd expect from the population? For a single qualitative variable, you're comparing observed frequencies to expected frequencies. So say you recorded handedness as a categorical variable in your sample. Chi-square goodness of fit test could check if lefties, righties, and ambidextrous people appear in the expected proportions. For one continuous variable, you're comparing your sample mean to a known or hypothesized population mean in parametric tests, or to a statistic like the median in non-parametric tests. For example, you might measure average IQ in a group and run a one-sample t-test to see if it differs from the population norm of 100. Or test sleep duration in a sample of undergrads and see if it differs from the recommended 8 hours. Next up, what about when you have two variables? Most classic tests live here. If both of your variables are qualitative, an example of paired samples might be testing whether the proportion of patients that correctly identify facial emotions changes before versus after a training program. Here it's paired samples because the same people are measured twice, and qualitative because it's a binary, correct-incorrect outcome variable. Or maybe you want to know if sleep quality, rated as good or poor, is associated with class year, like freshman, sophomore, junior, or senior. That's a chi-square test of independence. If your expected counts are tiny, you would use Fisher's exact test. Now, if both of your variables are continuous, like hippocampal volume and memory scores, a correlation would tell you whether these variables are associated. And when one variable is continuous and one categorical, first, you need to check how many groups your categorical variable has and whether your samples are independent or paired. For example, if you were comparing cortisol levels in a control group versus stress group, you would perform a t-test for two independent samples, or a Mann-Whitney U. However, if you were comparing cortisol levels in the same people after a relaxation condition and a stressful condition, your samples would be paired, since the same people were tested twice, and you'd do a paired t-test or a Wilcox-signed rank test. What about if you have more than two groups, like comparing working memory scores in children, adolescents, and adults? For this, you'd use a one-way ANOVA, Welch's ANOVA, or Kruskal-Wallis test. But if you had paired samples, like testing the same people over time, you'd perform a repeated measures ANOVA or Friedman test. Finally, when you have more than two variables, you're in what we call multivariate territory. Here, the key is your dependent variable. That's the outcome you measure. Predictors can be quantitative, like caffeine intake or stress levels, or qualitative, like sex or treatment group. And they can be combined in the same model. But if your dependent variable is quantitative, like predicting attention scores from sleep hours, caffeine intake, and sex, you're running a multiple linear regression. If your outcome variable is qualitative, like predicting whether someone develops depression, which is a binary yes-no, from a set of predictors like stress, social support, and whether or not a family member has depression, you'll run a logistic regression. Or you might be predicting three groups, like clinical depression, subclinical depression, and no depressive symptoms in the case of a multinomial logistic regression. Now this chart is missing a key branch here. What about when you have more than two variables and they are not independent? Here is where mixed effects models come into play. These models allow for hierarchical nesting, so you can account for repeated measures or other study designs where participants are linked. So when you're trying to figure out how the heck do I analyze my data, just follow this simple flow. How many variables do I have? What type are they? Are my groups independent or paired? Does my data meet assumptions? And then the test pretty much picks itself. All of these choices lead up to one big moment in your analysis, the p-value. Yes, the infamous p-value, sometimes misunderstood and misused, but often central to how we decide if our results mean something. So let's set the record straight. What the heck is a p-value? A p-value tells you the probability of seeing your results, or something even more extreme, if the null hypothesis were true. That means what's the probability of finding an effect where there really isn't one? If your p-value is low, usually less than 0.05, it means your result is unlikely to be just by random chance, and you might have something real on your hands. But here's the catch. A small p-value doesn't mean your finding is important. For example, a tiny change in blood pressure might be statistically significant but not clinically meaningful. This is why researchers also look at effect sizes, which tell you how big or meaningful an effect really is. So for example, a program might significantly boost reading scores by a few points, which is a small effect, or by whole grade levels, which is a big effect. And there are confidence intervals, which give you a range of where the true effect likely lies. They help you understand the precision and reliability of your estimate. On the flip side, a large p-value doesn't mean there's no effect. It might just mean your study didn't have enough power to detect a smaller yet meaningful effect. So for example, a software update that saves employees 5 minutes a day might not produce a statistically significant result in a small sample, but could add up to major productivity gains across a whole company over time. And one more important caveat. If you run lots of tests, say checking many outcomes or groups, your chances of finding a significant p-value just by luck go way up. This is called the multiple comparisons problem, and there are ways to correct for it, like the Bonferroni correction, to avoid false positives. So remember, p-values don't tell you the size of the effect or the direction or how well the study was done. Use them wisely, and please don't p-hack. That's when researchers run lots of tests or tweak decisions just to find a p-value below 0.05. It's just bad science. So the next time you're staring down a spreadsheet thinking, is this anything? Remember, know your variables, pick the right test, check your assumptions, and interpret results with context, not just chasing that p less than 0.05 badge of honor. In the next episode, we'll take the next step from understanding the logic behind these tests to actually running them in R. So be sure to subscribe to see if there's a positive correlation between watching Unhidden Curriculum and finally understanding stats. Thanks for tuning into Unhidden Curriculum. Until next time, stay critical and stay curious.